Yeah, cool. Okay, so thank you for coming. We're gonna start now because I only have 30 minutes to talk, so it's gonna be really, really fast. So I'm Francesc Campoy. I work for Google. I'm a developer programs engineer for the Go team. And today I'm gonna be talking about how Go makes your code grow in a very easy way. We're gonna start at a very, very simple example. We're gonna end up writing a whole server with concurrency features. So, first of all, how many of you have heard of Go before? How many of you have used it and programmed little things? Okay, that's good. So, as you may know, Go is an open source project. It's now 3 years old, and we're delivering the 1.1 version next month. The 1.0 was the first version that was completely stable, and it was delivered last year. Since last year, we've been basically working on making the language faster. So Go is about 3 different things. Go, first of all, is about composition, and we're going to see how exactly, but one part of the composition is the fact that it's object-oriented, but it's not object-oriented the way you could think about. We don't have the class keyword or inherits. We don't have inheritance, or we don't even have implicit implements. But we do have interfaces. Interfaces are a part of Go, but interfaces are satisfied implicitly. We'll see later how that helps to develop our systems. Go is also about concurrency. So we'll see the 2 features that Go, the 3 features actually that Go introduces for concurrency. And finally, Go is also about gophers, like in my t-shirt and someone else's t-shirt in the public. So we're going to be talking about composition, concurrency, and gophers. So first of all, to be very original and surprise you, a Hello World example. So I guess that most of you have already seen some Go code, but basically here we're importing the fun package, fun, which is short for format, and we're calling the function println from that package. So if we run that, 1 second. Whoops, my server died. Should be this one. No. Okay. Okay, there you go. So now we start with something more interesting already, since you have already seen Go. This is a hello.net. So what we're doing is we are listening from one TCP port, in this case localhost 4000, and every time that we can accept a new connection, we just print hello into that connection, and we close it. So if we do a little demo, if we do a net connect to there, we're going to just see hello, and the connection is closed automatically. Something interesting is that we're using the fprintln function, which is part of the fun package, and the first parameter for that function is a writer. A writer, it's an interface also that contains only one method, write, and actually any type implementing that method is by definition a writer. Okay, we don't have to say explicitly that type is a writer. That also means that other interfaces having at least that one method also are a kind of writers. So for instance, connection has read, write, close, and some other methods that we don't care about. Therefore, every connection is also a writer. Okay? So that's why we can do with C, which is a connection, we can call fprintln. Now changing just a little bit this code, we can do an echo server. What we're doing is pretty much the same, but instead of just printing as before, we call copy. Copy receives two parameters. One is a reader, the other one is a writer. Connection is both read and writer, so if we pass it twice, what we're doing is reading from the connection and writing back to it. So we have an echo server. So if we run it now, you can see, basically just echoes anything I say. Okay, now, can you see a problem that could make this not be a good production code? There's a little problem here. What if by any chance our company has more than one customer at the same time? That may happen. If we try to do that, so the first one will work, but the second won't work. What is happening here? Well, our first copy didn't finish, so we're still blocked there. So there's a problem here. We should create a new thread, a new worker for every request, so we can accept as many connections as we need. So to do that, we're going to use Go routines. Go routines, you can think about them as a very, very cheap thread. It's not exactly a thread, but from a conceptual point of view, an approximation which is good enough. With the little difference that you can be actually running hundreds of thousands of Go routines in a single process, and that works. If you try that with threads, that may not work. Okay, so to use Go routines, what we have to use is the keyword Go before a function call. So this is basically a function call, as before. And when you add the Go keyword, it means execute this in the background, or otherwise start executing it and continue your flow of code without waiting for that function to return. Okay? So in say, what we're doing is we sleep for the number of seconds that we were asked to sleep for, and then we print a message. So if we see this code, the third line waits only for 1 second, so it's the first one to be executed. Then the second message is 2 seconds later, the first one is 3 seconds later, and at the end, 4 seconds later, we finish. What would happen if we don't sleep? Well, if we don't sleep, nothing happens. Why? This because all Go programs start at the main function of the main package, and they start when the main Go routine, which is the one that started that, dies. So in this case, we start 3 different Go routines, one per say function, but since the main function finishes, we also finish and we don't stop. We don't wait for the rest. Okay. So now we have a concurrent echo server. Yes.
Question: does this mean that functions that you call with Go, while they're declared as functions, they don't have return types, or at least not ones that you can collect?
They can have return types, but if you do Go that way, you cannot collect them. You could use an anonymous function inside, and then do some things with that return. I will show a code of example doing exactly that. Okay, so if we compare the code from the echo server to the concurrent echo server, there's only 3 characters that change. It's G, O, and the space, and that's it. Basically, now what we're doing is, for every connection that we accept, if nothing bad happened, we do that checking if the error that it's returned is nil or not. If nothing bad happened, we start a new copy in a different Go routine. Therefore, the next step in this algorithm will be to be able to accept new connections again. So if we run this now, and a second one gets here, there you go. Now we have 2 different Go routines working. Okay. Now, who has heard about Go, chat roulette? Okay, surprising small number of people. So chat roulette is a chat server where you don't choose who you talk to. Basically, you connect there, and you get matched to someone else in the world. And we're going to do exactly that, but with text only, because we're in a demo, and doing that with video would be dangerous. So what we're going to be doing is actually very simple. Chatting between two different connections is basically just calling copy from one connection to the other, so there's nothing difficult about that. The difficult part is actually choosing the match. So matching two different connections in a thread safe way. So let's see what we had till now. If you see on the left, you have the echo server. So we have our main Go routine. Every square box here represents a different Go routine. So our main Go routine that does accept all the time, and every time gets a new connection, starts a new the function copy in a different Go routine. So this is the schema that we have so far. What we're going to do is something pretty similar. The main function is going to be doing exactly the same, doing accept, and every time it does accept, instead of calling copy, it's going to be calling match. And when we have at least two different Go routines trying to match, somehow we're going to be able to make them communicate and choose only one that is going to handle the copy in both directions. Okay, so to do that, we have to make Go routines communicate. To make Go routines communicate, we have channels. Channels, you can see channels as typed Unix pipes. So you can pass you can have any kind of channel. In here, for instance, we have this example. We have a channel of integers. And this is the way to declare them, using make. And you have two different operations. One is this one. So in here, we're putting a value j into the channel. That's writing into the channel. And you can also have this. That's an expression. And that's the expression that you will get the value that you read from the channel, in this case. Something that's interesting is that if you read from a channel and the channel is empty and nobody's writing, you cannot do anything. You have to block, by definition. But also when you try to write, if the channel, if nobody is ready to read from the channel, you also block. This means that actually channels are not only a way to make Go routines communicate, but also a synchronization system. So in this case, if we run this, we're running this fibs function that generates Fibonacci numbers. 1 second. And it's writing all these values into the channel. Every time that it tries to write a value into the channel, it will block till the main Go routine will get here and will read. The moment when we have someone ready to write and someone ready to read, we go on with the operation. Yes, did you have a question? No? I thought you had a question. Okay. So something that we need in addition to this is that sometimes you want to do more than one operation at the same time. So on channels. To do that, we have select. So the select statement is something pretty similar to a switch statement, where you have different conditions, but instead of having conditions, you have channel operations. And when you get to a select statement, you will evaluate all the operations, and from all of those operations, channel operations, some of them will be blocking at that time, and some of them will be allowed to be executed at exactly that moment. From all the ones that are ready to be executed, we choose one randomly. If none is ready, we will block, except if there's a default case. If there's a default case, that's the thing that you will execute when none of the operations is ready to be executed at the moment. So in this case, we have two different values here, two different variables, ticker and boom. Ticker is a channel of timestamps, and it will get a new value into the channel every 250 milliseconds. Boom, it's also a channel with timestamp, but it will send only one value after 1 second. So if we run this, we're going to be looping forever. So this is an infinite loop, which is pretty short. And then every time, in every loop, we're going to have this select, and we're going to try to read from both ticker and boom. So at the beginning, nothing will be ready, so we'll block. We'll block there until we get the first tick. And then we'll go on doing that until the fourth tick. On the fourth tick, you will get the tick and the boom at the same time. At that moment, we choose randomly which one will be executed. So we may get 4 ticks and a boom or 3 ticks and a boom, depending on the execution. So if we run it, there you go. Curious if that... Yeah. That's what I was saying. That's random. The 4th tick gets at the same time with the boom.
Oh, right, because you're returning after the boom.
Yeah. Yeah, once you get a boom, you're done. Yeah. Okay, so let's see how we could use... Yes?
I have a question about the syntax on the previous slide.
Sure.
I noticed that in your select, there's a method or some kind of internal thing called the .c. What is that?
.c is actually just a field from the ticker value, and that's the way you are reading from. So ticker is a type that contains a channel, and you're accessing to that channel.
Okay. Whereas boom is simple enough.
Yeah, I actually don't know. Yeah, so this is the channel. So there are slightly different types. They're not the same type anyway. One gets only one value, the other one is.
Well, it's a constructor, so it's, well,
Yeah,
kind of,
they're slightly different.
more complicated. Okay, thank you.
No problem. So what we're going to do on the main function, we're going to modify only one thing, as I was saying before. Instead of copying from one connection to the same one, what we're going to do is start a match function. And that match function is the interesting part. Okay, so what we're trying to do is to get two different Go routines, 2 different actors to interact, and only one can win. And the one that will win will get the 2 connections, and we'll start the chat function. The chat function will do all those copies. So the important part is actually choosing who is in charge of doing the chat. To do that, we have this variable. This is a package level variable, which is a channel of read-write closer. What read-write closer, we'll see later. But basically, because for our chat function, what we need is be able to read, to write, and to close the connection at the end. So that's everything we need. So instead of saying a specific type, we can say that interface. That's the interface that we care about. And then match, what it's going to do is going to try to put his connection into the channel and also to get a connection from the channel. So that means that when we have 2 different Go routines that will get there at the same, well, that will eventually get there, the first one will block because there's nobody there, so you cannot read or write. But the second one, it will try to read and write at the same time, so both operations will be ready. So randomly, we'll choose one. And that one that is chosen will imply who gets the connection. So in the code, if we are able to put the connection to the channel, we consider that we're good, and we exit the function. Otherwise, if we get a partner, we are in charge for executing the chat function. Finally, the chat, something very simple. We just write using println into both connections, notifying the user that there's someone ready to talk with him. We start a copy from A to B in a different Go routine, and we start our copy from B to A in the same Go routine. We could do it in different Go routines if we wanted, and then wait. That would work too. So okay, it's going to be a little demo of this. So I'm running exactly that code. Now, this first connection created this connection that was accepted, and now we're blocked in that select. We're trying to put the connection into somewhere, into that channel, and getting something from that channel. But since there's nobody else, everything is blocking. So we just wait. And as soon as the other the other connection gets there, the operations work. And we actually we don't know which one of the which one of the Go routines won that match and got the 2 connections, but we don't care. The connection is working both ways. So now it works. But what happened here? So, sad guy, he doesn't know that the other person left. Why? This is because we didn't handle the errors. So one of the connection was closed, but our second copy function is still working. We didn't stop it. So we have to modify that. Let's see how to do that. So we have to do error handling. Error in Go is actually an interface. It's an interface that is part of the built-in package. And it has only one method, which is error, that returns a string, saying basically what happened. So what we're going to do is implement our own copy. Because actually what we want to do is we want to care about the result of that copy. If the copy returns an error which is not nil, that means that something bad happened. But we want to execute that function in a different Go routine, but still we care about the result, which is exactly what you were asking before. How can we do it? Well, we can do it with a channel. So what we do is we create a channel of errors, and we pass that to the copy functions. So both copy functions start their copy, and as soon as they finish, they write the error that may be nil into the channel. Then we're actually waiting here for the channel, so we're reading from that error channel. We're waiting for something. And as soon as one of the Go routines finishes and sends the error, we'll check it, and if it's not nil, it means that something bad happened. So we will print it. But anyway, the important thing is that the Go routine, one of the copies finished. So one of the connections is closed. So we should close the other one too. So we call close on A and B. We're actually closing A or B twice, but that's something that works. There's no problem with that. You can close twice the same connection, and there's no side effect to that. So, really fast demo. Now, if we close this connection, the other one also gets notified. The connection closes. Okay, finally, and very, very fast, I don't think that anyone, well, maybe in this room someone still chats over TCP, but most of people don't chat on TCP anymore. They do it on the web. And the way to do it on the web would be using WebSockets. So I won't get exactly on. So this is a whole web server written in Go. We're using the net HTTP package. And the important thing is that we are declaring a handler for every URL matching /, which is all the URLs. And then we start handling, listening to the connection and serving. So basically, we start the HTTP server. Every time that we get a request, handler is executed, and handler is defined here. And we just do hello web. So if we start running it, no, have to stop. So if we start running it, and I go here, there you go. This is our web server responding. Now, we can also have WebSockets. WebSockets are very similar, but we will use the WebSocket package, which is here in go.net, which is part of the Go repository, actually. And that allows us to read messages from so we get a connection, and we can read from that, and write into that, and also close it. So I won't do this one, but you can use both at the same time. Okay, you can have standard handlers and WebSocket handlers. The way to do it is just defining twice a handler. The first time is, as the first one, root handler could be just a function with a good signature. The second one, we're actually returning an object created by the WebSocket handler adapter. Okay, then we have also the HTML templates. Go has an HTML template language that is very interesting, but we won't see it today. The important thing here is actually, at some point, we're using this syntax. This syntax means put the value of the parameter that you got in there, and we're going to pass the URL to the server, basically. And I don't think we have time enough to explain how this works, but we're able to create a new type. So this type is a struct containing a WebSocket connection and a channel. The WebSocket connection is used to do read and write. So if someone calls read on this socket type, we use the read from the WebSocket. If someone calls write, we call write to. And if someone calls close, then we just put a value into the channel and return. Actually, why do we do this? This is a way to allow the socket handler to wait for us to be done. Because if otherwise we wouldn't be waiting, and the WebSocket connection would be destroyed as soon as the socket handler function ends. So the way to make this wait till the connection is closed is actually waiting for a value from that channel, and the only way to write a value into that channel is actually calling close. So if we take our connection from before, our algorithm from before, at the end of the chat, we'll go close, and that close will be this one for our socket type. Okay, you can actually be slightly shorter, but we won't get into that. So I won't do the demo. I prefer to do the questions. And one last thing is, okay, we've done composition with types. We started with just TCP connections. You can also use WebSockets. In the whole version of the talk, I also use a bot. We create a bot that is able to learn how to talk, and we don't change anything in the algorithm. The algorithm stays always the same because it's using the interface open, closer, no, read, write, closer. And everything that implements those three methods is a good type for our algorithm. Another way to do composition is actually using composition of processes. And that's very easy with the Go routines. Actually, so this is the function that we got for the HTTP server that declares the true handlers and starts the HTTP server. This is the one for the TCP server. Well, if we put the TCP server into one function and we call it in a different Go routine, there you go. We have now an HTTP server and a TCP server working all together. So now, if we do the little demo and we execute both, there you go. So now we're talking through a web server, and the messages are received into the TCP. We don't change anything from our algorithm, just adding composition and making our code grow using both types of composition. Composition of processes and composition of types. So that's all for my talk. So thank you very much. If you want to learn more about Go, you can go to golang.org. That's our homepage. The slides for this talk, which is slightly longer normally, are here. And if you're interested about more concurrency patterns, there's two talks. One that is already created, which is concurrency patterns by Rob Pike. And for Google I/O, we'll be having also a different talk, which will be actually the second part of concurrency patterns. And if you want to contact me, that's my email, and on campo.cat you will have links to Google Plus and Twitter. Okay, thank you very much. And if you have any question, okay, maybe we can. There you go. Ooh.
I'm going to make you run even more, maybe, because.
There we go. Could you go back to the slide for the simple TCP server where you were calling send? Let's see, or you were waiting on a send.
Yeah,
not the echo server.
This one here, maybe?
Yeah, okay. I'm sorry, not send. That's the timer. That's the countdown.
This one.
There we go. Case, partner. Okay, you said it's not deterministic which one of those will be executed first?
No.
Okay, because it's a select. So what I didn't understand is why you don't run, in this case, a 25% chance of deadlock. For instance, if they both select the first case, wouldn't they both be waiting on the other to execute?
Because there's two different operations.
Okay.
And the one you're choosing, it's random. But once you execute one, the other one will be the only one to be able to be executed. So if, for instance, A gets to write into the connection.
So this is blocked on both channels.
Yeah.
But as soon as one comes available, it'll kick the handler.
Yeah.
Okay, got it.
Any other question? Yes?
You said the Go routines are very lightweight. What's behind the scenes, like a user space bridge on this?
So if you know what a coroutine is, it's a very similar concept. They are handled by the Go runtime, not by the OS, and changing from one to the other is actually done by the Go scheduler. So it's actually very optimized to handle that. And the Go runtime, it will be able actually to schedule different Go routines into different channels to make them, so if there's into different threads, sorry. So if there's a thread that blocks for I/O, and it has to because of the implementation for the OS, the scheduler will take all those Go routines that were there and move them to a different thread to allow them to keep on running. Yeah. Any other question? No? Okay, thank you very much.